Okay, so today we're going to look at concavity in the second derivative. Yesterday we talked a little bit about the first derivative test. As you can see labeled in this picture, it says concave up. So I'm going to give you some of the information ahead of time and we'll talk about what this means. In calculus we say something is concave up if the second derivative is greater than 0. And an example of this, here's a concave up graph. Here is a concave up graph. I usually do this by making weird gestures with my hand like this and like this to talk about concavity. So don't think it's weird if I'm working out questions and I'm going like this on the board. You're welcome to do this on your tests and quizzes too. It actually helps a lot at figuring out whether it's concave up or concave down.
For secondaries, you have to pick up the shadow.
Maybe if I move it really fast. So, anyways, you're thinking of a cup, right? So concave, like when you talk about lenses in science and they say concave, you want to think of the cave. Well, there's my really bad cave, right? But concave up means the cave is this way. Concave down means the cave is pointing down. So let's talk about why that is, and we'll talk about x squared here. So if you think about this derivative, I mean, it's shown in these little faint pink lines, right? So there's the slope of the tangent line. As I move from the left side to the right side, here's what's starting to happen to that tangent line. So we're going from very steep negatives, like this, to smaller negatives, and eventually we end up hitting 0. So we went from negative to 0, and then we went from this side where it's equal to 0, small positives, getting bigger, we're getting much, much larger. So basically what's happened is the first derivative has gone from very large negatives to very large positives, so it's increased that whole time. The only way to get from negatives up to positive is if you increase all the way up. So we're talking about the rate of change in the first derivative. That is the second derivative. That's why if the second derivative is greater than 0, we end up getting these shapes of concavity in the graph. Okay? So similarly, if we were to talk about concave down, the second derivative would have to be negative, and some pictures that you might see, you know, something like that. The log graph, stuff like that, are going to be concave down. Okay, so the process that we've been talking about for the first derivative test, we're almost going to repeat that today when we talk about concavity, only we use a little different term. So when we're talking about first derivative, what did we call those special places? Critical points, yeah, our critical numbers. So when we talk about those special places in the second derivative, they have this new term now which we call inflection points. Okay? So an inflection point, it's somewhere that we have the second derivative equals 0 or is undefined. So that should sound really familiar, right? Just like the critical points. And we're going to follow the same process. The first thing we did was let's find those inflection points. Then we would make a number line. And then we wanted to figure out where it's positive and negative. Because to us, positive is concave up and negative is concave down. So we're going to do much the same process, but today we're talking about second derivatives. So here are some pictures of what you would expect to find when we talk about these inflection points. So I'll put them into the picture here. Okay. Those 3 red dots are inflection points on those graphs. Now inflection points aren't always easy to find because it's hard enough to think of the derivative in a graph. Now you have to think of the second derivative just by looking at this one. So it's really, it gets kind of tricky. So again, I would make these weird hand gestures and trying to make curves and things out of it. But what I'm trying to do is figure out where does my hand have to change. So for example, I can see here that this is concave up, but then all of a sudden I'd have to get my hand back around the different way, it had to change in order to do that. So where did it change? That's the point at which the graph has changed from concave up to concave down. And similarly in these other examples, right? Here's one where the graph is undefined for its tangent. Okay, so it's also going to be included, undefined and included as our concavity. But you can see it's a place where we go from concave up to a place where we go concave down. So let's try and find some of these things in a graph. Today we're just, or for this first one, we're just going to find inflection points. Okay, so don't worry about talking about concavity, but we'll verify it with the picture in the graph. So try this first one here, just using, trying to find the inflection points of the graph. So you might not quite be finished, that's fine. Take a couple minutes here. I'm just going to start working out my solution. So now that we're getting into not just the first derivative, it's important to remind yourself too, what exactly are we looking for here? First derivative means we're talking about critical points, extrema. Second derivative means we're talking about concavity. Okay? So try and keep those distinct in your head when you're working on these. Remind yourself, I'm looking at the second derivative to tell me about this graph's concavity. If I'm talking about extrema, I'm going to be looking at the first derivative. So I'm going to show you a picture of this graph. Okay, so this is the graph y equals x to the fourth minus 4x cubed. And I'm going to have to change that a little bit. So let's go, okay, so there's a better picture of it. So as you can see, we said 0 and 2 were the points of inflection. So let's take a look here at 0. You can see that it goes from concave up on the left side. I'd have you holding my hand this way up, and then it goes to concave down. Now it's not as obvious that it changes at 2, where we found that other answer, but what you can see is I'm holding my hand down at this side, but then somewhere along the way I have to change it. It has to go back up. So somewhere between where my, let's go, left hand and right hand meet, there has to be a change, a point of inflection. So 2 is where we found it algebraically. It's easier to see it algebraically sometimes than visually. But somewhere right about there, it's going to change from down to up. Okay? Okay. So let's take a look at the next one. And we want to talk about the concavity of this graph. So this time I want you to go through the full second derivative test. Find your points of inflection, make a number line, then tell me about where it's concave up and where it's concave down, and again we'll verify it on the graph. Okay, so I realize that's not quite enough time to finish, but I'm going to just try and catch up a little here. So I believe it'd just be negative x because when I use the power rule, that 2 and that half would cancel out, right? It would be 1/2 times negative 2x. So it should end up just simplified to negative x. Okay, so second derivative is going to be a product rule. So let's see here, we got negative, so it'll be e to the negative x squared over 2 plus x. And this piece that I'm trying to differentiate here, that's the original function. So if you catch that, you don't have to actually do the derivative again. You can just reuse your answer. So my answer for that one was negative x e to the negative x squared over 2. So I'm saying the second part of the product here has this derivative because I know that from the first part of the first derivative. So if I try to tidy this up a little bit, I'm going to factor out this e to the negative x squared over 2. And I guess there'll be a negative there. So there'd be 1 minus x squared. And that means I'm not going to be able to make this piece here equal to 0, but I can see some candidates at plus or minus 1 that could make the whole thing equal to 0. So that means I'm going to have these pieces, negative 1 and positive 1. And again, I stick to the table method, but remember what you're putting in as your function is this here. You're putting in the second derivative because you want to know, is the second derivative positive? If it is, it's concave up. Second derivative negative? If it is, it's concave down. Okay. So I believe, and somebody can hopefully verify that for me, I believe is that we get positive, negative, and positive?
I feel like it doesn't look right.
Yep, that is right, what you have on your screen there. Okay, so I'm going to show you the picture just to verify that this is making sense. So let's remove that. Let's go y equals negative, e to the negative x squared over 2. And of course I'm going to change the range on this. Yeah, so there's a picture of the graph. And where we predicted was over here at negative 1 that there would be a change, and over here at positive 1 that there would be a change. So you can see it's concave up as I approach from this side here, concave up, and then it switches. This is a concave down section. Switches one more time. This is a concave up section of the graph. Okay. So it does agree with the number line, so I think we're correct there. Okay. How are we doing so far? Going too fast, too slow, just right? Goldilocks? Somebody got it, okay. Okay, so then if we wanted to put this in, this is concave up, concave down, concave up, and those are my inflection points at plus and minus 1.
So that's the answer. This is the
Concave up, concave down. Those are the abbreviations that I'll be expecting because we're all lazy mathematicians and we don't want to write concave up and concave down in our homework. Okay, so are we okay to move to the next one? Okay. Algebra. I'm going to use a little bit of, I'm going to use an extra sheet for this one, but I'll give you guys a couple minutes to try it. Tell me about the concavity of this one as well as its inflection points. Okay, so I'm going to do this on a separate sheet just so I can have some extra space. So the function is x squared plus 1 over x squared minus 4. Okay, so deep breath. And here we go. F prime is going to be the derivative of the top times the bottom. Take away the top times the derivative of the bottom. Okay, so if I try to tidy this up, I'm going to get 2x cubed minus 8x. Take away 2x cubed minus 2x. And x squared minus 4, all squares on the bottom. So if I tidy this up, collect the like terms, first derivative should be negative 10x over x squared minus 4. Okay, so I'm going to leave that there, but I'm going to start the second derivative. Okay, so for the second derivative, derivative of the top is negative 10. The bottom, take away negative 10x times the derivative of the bottom, which is, oops, it's going to have a chain rule here, so we're going to have...
I think you just expand x squared minus 4 squared.
You certainly could, but I'll show you why I think it's easier to do it with chain rule in just a second. So 2x squared minus 4. Where are we now? Okay, so that's the outside, and then this is the inside. So there's the derivative of the bottom, and it'll be all over, I can do a better line than that, it'll be all over x squared minus 4 to the fourth. So the reason I left it in factored form is I'm going to need to do some factoring to simplify it here. So for example, this piece is all out throughout this example. If you try and expand this stuff, you're going to have these terrible numbers like x to the 4, x cubed. You're going to have lots of extra stuff in there. So it is better to keep things as tight and compact as you can until you absolutely have to expand them. So for example, if I factor out x squared minus 4, that means, let's see here, I'll have x squared minus 4. So I'll have negative 10 x squared minus 4 plus, so there's 2x, 2, and 10, so that'll be 40x squared. And then on the bottom, x squared minus 4 to the fourth. And of course, one of those there leaves me with 3 of them there. So the second derivative, let's see here, that'll be negative 10x squared minus 40 plus 40 x squared all over x squared minus 4 cubed. So the best I can do with the second derivative, oh sorry, yes you're right, it's positive 40. The best I can do with the second derivative, I believe, will be like this. And one thing we should be careful about here, remember, anytime we remove information, we might remove some of our answers. So I'm just going to put a little purple star here. Because now if I want to look for where this equals to 0, if I look at the top, I would say there is no place where this derivative, second derivative equals 0, because the 3x squared would need to be negative 4. So is there a way to make this negative 4? No, we can't get negative numbers out of something when we square it. So that means that's not an option. So the only other place I could find my inflection points is underneath if I divide it by 0.
It should be negative 4.
Say again?
It should be negative 4 after 3x squared.
After 3x squared. Is it?
Because you take negative 10. Everything's negative.
Oh, because I took a negative 10 out. I guess I was getting fancy. Okay. So apparently, yeah, that makes sense. Thank you for that, Eamon and Andy. So apparently there is an extra place here. Okay. You know what? I think I need to, if I went too quick there, I'm going to have to double check. So I'm going to pause this for a second. Okay. So apparently, I think I was looking at this here, not realizing that it was going to turn into positive 30. I think I was... Anyways, so there's no reason I should have taken that negative out. It should have been as I had it, but with a positive 10. Okay. So that means same thing as we don't have a solution on the top. On the bottom here, though, I can find some inflection points at x equals plus or minus 2. So let's draw our number line at negative 2 and at positive 2. Now, as I had said, you have to be careful when you're removing that information. If we would have removed it completely from that equation, then we might be tempted to say there are no inflection points, right? Like if there was an x to the 4 that I factored out on top, and I took everything out, right? Then we would have had nothing in the algebra. But remember, you've actually gone and changed the original. So in this instance, it works out the same, but be careful when you're canceling stuff out. I think we talked about this also in like trig equations, why some of your solutions disappear. So in this instance, here's our number line where we can talk about concavity. So in the first region, what do we have for the concavity of this as my function? Positive or negative? Positive? And then I'm assuming... Okay, so let's take a look at the picture and see if we're anywhere close to what this should look like. So y equals x squared plus 1 over x squared minus 4. And let's change the range here. Okay, so here's the picture. And again, if you look at positive and negative 2, that's the asymptotes on this graph. Okay. So here's, whoops, no thank you. Here's where the graph changes concavity at positive, negative 2. You can see on this side here, it's concave up. Then on this part here, it's concave down. And in this section here, concave up again. So that's what we predicted, concave up, concave down, and concave up one more time. Okay, so the last thing we're going to talk about today is how concavity can also help with the maximums and minimums we've already talked about. So for example, if I have a concave up graph, it's going to look kind of like this. So here's concave up. And let's just say that I found some extrema. What can you conclude about that extrema? It's got to be a minimum. So if you think about it, if it's concave up, your extrema there would have to be a minimum, right? Because of the way the graph is shaped there. Similarly, if it's concave down, that means we have to be talking about a maximum. So the second derivative can also tell us, we don't have to use the first derivative test, we can also try using the second derivative. If a critical point is a relative minimum, that means the second derivative, okay, for a minimum, it has to be greater than 0. The graph must be concave up. A critical point is a relative maximum if the second derivative is less than, oops, forgot my x in there. If the second derivative is less than 0. In this case, meaning that the graph has a picture where it's concave down. So that's like this example up here. Now, what happens though if it equals to 0? It's an inflection point. Yep, that's correct. But can we say anything about whether it's a minimum or maximum? Here's some pictures to jog your memory and see if you can figure out. There's the 3 inflection points I showed you earlier. What do you think? If that critical point you found also turned out to be an inflection point, what do you think? Is that a minimum or maximum? Well, what do you think from the picture? Let's just state the obvious case. No, it doesn't look like it in the picture. If you were to think about, like, so you take your really bad hand cup and you take the other one, that's the inflection point where my fingers meet, right? So if my fingers meet there, could that be the minimum or maximum, right? No, you can't, you won't get a minimum or maximum out of it as the inflection point. So that's what we can conclude here, is if it does turn out to be 0, it's not what we're looking for. It's not extrema. So I mean it's not a minimum or maximum. Okay. So let's try it here with this polynomial just to see what I'm talking about, how we can use this. Okay, so if we're talking about extrema, that means we need to use the first derivative to find critical points. Okay, so let's find those critical points. All right, let's see if I can redeem myself here. I'll try and take out I'll try and take out the negative properly this time. So this will be x squared minus 1. There, how's that look? Does that work? I think I got it factored right this time. So I would conclude then that I have critical points at x equals 0, 1, and negative 1. So at this point, you would draw your number line, you would make up a little table, you try and decide where it's positive, where it's negative. But I'm saying, let's try using the second derivative test instead. Sorry, and this will be x plus 30x. Okay. So when I put them in, the second derivative at 0 is negative 60 times 0 plus 30 times 0. So I end up with nothing. So what can we conclude about that critical point x equals 0? It's not extrema, okay? We'll look at the picture later just to verify all of this. Okay, let's see what happens if I go second derivative at 1. That'll be negative 60 plus 30. So I end up with negative 30. So tell me, if the second derivative equals negative 30, are we talking concave up or concave down? So what kind of extrema is that? A maximum, right? So nobody's going to laugh at you. You see me doing it all the time. If you do it in your quiz or your test, right? There'll be like 15 of the 30 of you going like this at some point in your test, but that's okay. So it's concave down, which means this must be a maximum. Okay. If we find the second derivative at negative 1, that's negative 60 times negative 1 plus 30 times negative 1. Turns out to be 30. So this time, what are we dealing with?
Concave up.
Yep, concave up, which means a minimum, right? So concave up, that's the minimum down there. Okay, so let's take a look at the picture and verify that the second derivative test works. It's quite a waste of your time if I just drag you through all that calculus without it, but let's still verify it. So negative 3x to the 5th and plus 5x cubed. So let's just go... Okay, so there's a better picture. And here's what we predicted. At negative 1, there would be a minimum. Okay, so that's the minimum right there. We predicted that at 0, it would not be a extrema. It wouldn't be a minimum or maximum, and that's true there. There is no interval for which that point turns out to be the smallest or largest place.
So is that the inflection point?
That is an inflection point, yes. You can see the concavity changes from down to up, right? So that's why it equaled 0, but it means it's not going to be extrema. Okay, so then here, this is our maximum that we predicted would happen at x equals 1. Okay, so there it is from the second derivative test instead of number lining it. Okay, so that's us for concavity today.